Can you all hear me? Great. Good morning. So my name is Kate Heddleston, like he said, and today I'm going to talk about Python and technical debt, and I wanted to open with a story from another person's talk. So I saw this talk recently called How Language Shapes the Way We Think by a researcher and professor named Lera Boroditsky. And in it, she tells a story about some time she spent with a group called the Cook-Theory people, and they live in a somewhat remote part of Australia. Now, what's interesting about the Cook-Theory people is that in their language, they don't use words like left and right. They describe everything in cardinal directions, so north, south, west, and east. This means that if you told someone to move their cup or that their cup was to the right of their hand, you would instead say, your cup is to the south-southwest of your hand. And this permeates everything about their language. So when you greet someone, you're supposed to ask them, what direction are you going? And the correct answer is north-northwest into the far distance, or north-northeast into the far distance. So as she studied this group, she found out something about them that was really interesting. We've always thought that humans didn't have any particular talent in orienting themselves like certain animals do. So some animals have magnets in their beaks, and as they migrate, they can tell direction in a way that is much more precise than humans. However, the Cook-Theory people have proven that through the use of language, they can actually orient themselves as well as animals that have magnets in their beaks. So in other words, because this is a part of their language, they are able to orient themselves in cardinal direction at any given time very accurately. So this got me thinking about, she has a quote in there that says, if you can't say it, you can't think it. And about 6 months ago, I started working at a new company, and we are built in Go, we use React on the front end, and we use TypeScript. So I've spent the last 8 years working in Python, and now I'm working in a new language. And so I was starting to learn Go, and I was going down an internet rabbit hole of talks about language and how it affects how we think, and I was like, how do programming languages affect how we think? And specifically, how do programming languages affect the types of messes that we get into? Because programming languages are really kind of as interesting as the messes and the trouble that you get into, in my opinion. So, for this talk, I decided to put together an exploration of Python and technical debt. And I'm going to talk about 6 questions that I've explored during my research for this talk. And I say explored because I don't think I came up with a lot of answers. I came up with a few things that I would do differently based on what I learned. But exploring languages and technical debt is really just that. And I highly recommend this. So next time you're hanging out with friends from different companies that work in different languages, ask them about the types of technical debt that they see in their language. It's great fun. So these are the 6 questions that I went through. What is technical debt? How do you even know if you have it? Why would you ever take on technical debt knowingly? When does it become a problem for you as a company and as an engineering team? What does it look like in different languages? And then finally, what can you do about it? So, my name is Kate Heddleston. I am a software engineer and engineering manager at a company called Shift. We are a marketplace for buying and selling used cars in California. So we actually don't have product scale. We have something I call product complexity. When you sell cars, it is a high-value, low-volume item. In other words, people don't buy cars on the scale of Facebook usage. But we have a lot of product complexity because the technology we're building is solving a very complex problem. So that makes our concept of technical debt very interesting. If you get bored during this talk, you can always check out kateheddleston.com/about and find out everything you never wanted to know about me. You can tweet at me at Heddle317, and you can generally find me on the web under my name. So first, what is technical debt? Technical debt people use as a somewhat nebulous term, but in a general sense, technical debt is the implied cost of additional rework caused by choosing an easier but more inefficient solution now over a better approach that would scale better long term, but would take longer to build. So there's 3 types of technical debt as defined by a bunch of blog posts that I read. The first is deliberate technical debt. Deliberate technical debt means that you knowingly take on technical debt. You are aware of what you are building and the difference between what you should be building, and you make a conscious decision to take on some technical debt in order to build faster now. This happens at early stage startups to a certain degree. So you might not know the kinds of abstractions that you're going to need long term. So you say, we're going to build something simple to solve the problem now. And as we learn more about the problem, we will rework our code to map to it. The second type of technical debt is accidental, so outdated designs. This is kind of a follow-on from often deliberate technical debt. As your company grows and scales, you might have built abstractions that worked for one problem. But as your company got larger, you realized, actually, maybe we didn't understand the problem fully, and so these designs are outdated, and they're starting to become a problem, because we actually need to solve for a different problem than we originally understood. And then the third type of technical debt, as I define it, which is very common in startups, and probably the most problematic, is what I call accidental technical debt out of ignorance, or miscategorization of a problem. So ignorance and miscategorization of problems means that if you had a problem that would be obvious to someone with 10 years of experience, but you have a team that only has a few years of experience, they might actually miscategorize the problem and build an inefficient solution, even though somewhat efficient solutions that are simple to implement exist. Does this make sense to everyone? This happens a lot in startups, where you have teams with engineers that might be a year or two out of school, so a lot of young engineers building very quickly, and they haven't necessarily seen a lot of the common design patterns in web applications, and so they build inefficient solutions that they wouldn't have needed to build had they had a bit more experience. So I also started taking a look at some of the design patterns that exist, because basically design patterns are a way of saying, hey, as a community, we've seen some bad stuff happen when we did things a certain way, and so here's a design pattern to help you solve a problem that we've run into a lot of times. So dependency inversion, dependency injection, composition over inheritance, unidirectional data flow are examples of this. So, for example, dependency injection. A lot of young programmers will get caught by having a bunch of dependencies inside of an object. So dependency injection is a design pattern that says, hey, instead of creating these dependencies inside of an object, why don't you just pass them in? If you pass them in, it's much easier to construct them inside of tests, so you're much more able to test the objects that you have. And once you know that design pattern, it's very easy to start using it more. But if you're unaware of these design patterns and the ways that they have gotchas, you can accidentally add a lot of technical debt to your code base that you didn't need to. So how do you know if you have technical debt? I started looking at the symptoms of technical debt because I think that's a little bit of an easier way to understand it. And I came up with 4 things that will help you know if you have technical debt. So if your code base has a lot of bugs, a lot of exceptions, that's technical debt. The second one is performance. And in web applications, performance often comes from things like network calls as opposed to the actual speed of the language. But in some languages, performance of the language actually matters. The third is complexity. Can your code be changed in a reasonable amount of time by an average engineer on your team? And then the fourth one is coupling and decoupling, so abstraction. Can tests be written for your code at all? So one of the biggest heuristics of technical debt is if you cannot test the code that you have. And to give an example of this, a friend of mine works on the Android team at a public company in Silicon Valley, and one of the things he's having trouble with is tightly coupled code. So in Android, there's the view, which takes in events from buttons on the screen, for example. So if you click a button, there's an event, and then something is supposed to happen. If you couple all of the business logic with that event from the UI effectively, it's very difficult to test because you have to run a simulator for the UI. So what you're supposed to do in Android development is decouple those two things so that you can test the business logic separate from testing the view code. So the fact that they cannot write tests because a lot of the business logic is in their view code is a really great heuristic that they have a lot of technical debt in their Android application. This is one of my favorite quotes. Programs should be written for people to read and only incidentally for machines to execute. There are a lot of things that machines don't care about in execution, but that people do care a lot about, and vice versa. But the biggest symptoms of technical debt often come from people having an inability to change code safely. So we are the weakest link in computers, and I think that's a really important thing to remember when it comes to technical debt. So why would you ever knowingly take on technical debt? I think this is a great question. Before I worked at the company I'm at, I had a small startup of my own. So we were a small team, we were building a product. And when you have a startup, the goal of having a business is actually to make money. And it's to get to something that's called product market fit as quickly as possible. How many of you have heard the phrase product market fit? You? It's a Silicon Valley buzzword. So what it means is you have rapid adoption of your product. And this is actually the sole focus of a startup. Startups don't care about code quality. They don't actually care about how well built something is. So this image here I have is of the Wizard of Oz. Has anyone ever heard the phrase Wizard of Oz? Wizard of Ozing something. So this is also a Silicon Valley buzzword. And it comes from the movie The Wizard of Oz. In the movie The Wizard of Oz, the wizard is pretending to be a great sorcerer, and he's tricked the people into thinking he's this powerful magician, but he's actually just standing behind a curtain, and he has a bunch of lights, and he's creating illusions that are tricking the people into thinking that he's a powerful sorcerer. So in software and in startups, when we say Wizard of Ozing something, what we mean is, can you make it work without having to build everything you need to actually make it work? So can you pretend in the background like this thing is actually functioning enough to prove out your business model? So as engineers, our goal is generally to build high-quality code, scalable systems, but as a business, your goal is very different. Your goal is to stay alive, and your goal is to get customers. So as an early-stage business, you might actually knowingly take on technical debt in order to prove out your business model and stay alive. So I often tell early-stage companies that there are 3 questions you should answer whenever you're building any feature. The first question is, should we build this at all? Or can you Wizard of Oz it? Can you fill it in with manual solutions? The second is, should we build this here? So if your business, and Netflix is actually a great example of this. Netflix's business is high-quality streaming video content to customers. And in 2007, 2008, 2009, when AWS was a new product, they sat down and they made a conscious decision to move to AWS from their own internal servers. Basically, they were like, our business is not maintaining servers. Our business is streaming video to customers. So we're going to move to AWS. AWS's business is actually maintaining servers. And we are going to pay them to do this because we think it will give us a competitive advantage. And while Netflix is one of the biggest consumers of AWS and they pay them a lot of money, it's allowed them to move quickly, it's allowed them to keep their team size small, and it's allowed them to focus on their core competency. So basically, in answer to the question, should we build this here, Netflix said no, we should not be managing our own internal servers for a lot of our solutions. And then the third question you should ask when you're building a feature is, how much technical debt can we take on, or should we take on in order to launch this? So if you decided, yes, we should build this for our business, yes, we should build this here for our business, then the third question is, how do we build this in a way that is scalable, but we can also get to market quickly? So when does technical debt become a problem? Now, I have a small personal website that I built myself, kateheddleston.com, and it's a Python application, and arguably it's not the most beautifully built Python application. It doesn't currently have any bugs. Its performance is fine. There's one engineer who maintains it. That's me. And I can go and change anything at any time. So do I have technical debt on my website? Maybe, but probably not. It's fine for what it does. So there's certain points at which something that you've built, the technical debt actually gets called in. And on my personal website, it's never been called in. So technical debt gets called in when something significant happens to your platform, your team, or your code base. So there are 3 kind of events that can cause technical debt to get called in. The first is system scale. So if you're starting to get a lot of customers and your system is actually scaling hugely, so let's say you went from 1,000 unique views a month to 1 million or 2 million or 10 million or 500 million, the scale can become enormous, right? And suddenly scale really, really matters. So performance matters, bugs matter, the way that your system is abstracted matters in a way that it wouldn't at a smaller scale. The second thing that can call in technical debt is team scale. So you might actually be adding engineers to your team faster than your system is scaling. This can absolutely be true today because there's a lot of solutions out there that can help you scale a product really easily with a very small team. So solutions like AWS make it possible for you to serve content to millions of people with a very small number of developers. But you could be growing your team quickly, and suddenly the complexity of your code and the readability of your code matters a lot because you have new engineers who are coming in and trying to make changes to an existing system. And then the third way that technical debt can be called in is product complexity. And it's interesting because this is actually what we have at my company. Like I said, we are not a system scale product. People do not buy cars in a volume that is ever going to matter for computers. So product complexity is our biggest challenge. And at product complexity, you actually kind of get all of the technical debt called in. So complexity, readability, bugs, not so much performance issues, but because what you're doing is complicated inherently, if your code is complicated to match it, you can have a lot of problems, and it can suddenly be very slow to change your complex system. One of my favorite systems quotes is actually, "There is no such thing as a small change to a large system." So, given that, what does technical debt look like in different languages? So this is where I started to ask the question, how does the language that we use shape how we think? As I said before, if you can't say it, you can't think it. So, like the Cook theory people, what types of things are we thinking a lot based on the languages that we use? So I kind of came up with 6 different areas. There's a lot of different areas. There's a lot of different ways you can compare languages. This is by no means a totally cohesive exploration of all the ways that you can compare languages. But I came up with kind of 6 categories: memory management, static versus dynamic typing, imports and namespaces, object-oriented versus procedural, community features, and then universal tech debt that you will get anywhere, because it turns out that you can make a mess no matter what programming language you use. And I also thought this graph was really cool. So the most in-demand programming languages of 2018 based on job postings, at least in the United States, it goes Java, Python's number 2, JavaScript, which is actually the most used language, by the way, C++, C#, Ruby, Perl, PHP, C, and Android are all in the top list of most in-demand programming languages. So first, memory management. This is an example that I thought was really interesting, kind of based on the cardinality of the Cook theory people's language. So when I was in college, we took a bunch of systems classes in C, and we had to do all of the memory allocation and cleanup. And I remember during my first systems class, during finals week, because I was really stressed about finals, I had a nightmare. And in it, I dreamt that I was a struct. And I had allocated memory for myself, but I had forgotten to clean it up, which meant that my brain was full and I couldn't learn any new information, and I was screwed for finals. And it was a very bizarre dream. But I remember thinking that I was starting to think in C, and it was giving me nightmares. So today, we actually don't use a lot of languages that do memory cleanup for web development, at least. I mean, C is definitely used in a lot of places. But for a lot of the new web development we use languages that do automatic garbage cleanup and handling. So kind of what are the differences in how we would think? Well, if you use a language where you have to do memory allocation, then you get really, really good at thinking about memory allocation. You can optimize performance, theoretically, to whatever degree you want. However, allocation and cleanup add complexity. So it takes up a lot of your brain space to think about allocating memory and cleaning it up. Whereas if you use a language that does that automatically for you, it can have performance costs. Certainly in the background, the garbage cleanup can have performance costs, and we know this, which is why a lot of gaming languages opt to optimize this. But it frees up a lot of developer time. So if you're doing web development where you don't actually need that kind of an optimization, Your developers shouldn't think about memory allocation because they should be thinking about other things with their time. Static versus dynamic typing. So working in Python, if you ever talk to other developers who work in other languages, people have very strong opinions about static versus dynamic typing. Now, Python is a famously dynamically typed language. And so I compared Python to the new language I'm working in, which is Golang. Golang is a new statically typed language that has some strong opinions about static typing. But kind of comparing the two types of technical debt, this was where I started to find some things that were really interesting. So Python is dynamically typed. You can do duck typing. And one of the kind of important things about that is there's no real concept of interfaces. If you've ever read a lot of design pattern books, yeah, that's a good point, I know. A lot of the design patterns talk about interfaces and decoupling interfaces, and we don't really have that concept in Python. Golang is statically typed. All right. Python is dynamically typed. Golang is statically typed. Some of the real advantages of statically typed languages is that go to definition is really fast. So in a statically typed language, you can go to the definition of a function call immediately. You can also see what arguments a function call specifically requires, and if you have any mistakes, obviously they're caught very early on. One friend also pointed out that another advantage of statically typed languages is that you can rename almost instantly, which means that if you can rename quickly, bad names don't stick around very long in your code base. So if you're going around and you see a name that doesn't actually describe what a function is doing or what a variable is doing, you can rename it. In Python, it's actually much more difficult to rename, so bad names stick around your code base for a long time. So statically typed languages, this is actually kind of well known in the community. Statically typed languages actually do catch a lot of bugs that humans make, so a lot of human error is caught with static typing. One of the advantages of dynamic typing is that it reads a lot more like English, so it's very readable and it's usually very quick to type, and it can be a lot more succinct. That being said, a lot of companies that use Python at scale are actually adding in typing. So MyPy is a Python library that allows you to add types to your Python, and they've been deploying it at Dropbox. I think they're at like 20 or 30% of their code is now statically typed because they found that this is actually a huge advantage. Imports and namespaces. So if you're comparing a statically typed and a dynamically typed language, those languages can look really different. But what about languages like Ruby and Python, which people think have a lot of similarities? And they do. They're both dynamically typed languages that are often used for web development, that have fairly strong opinionated communities. And one of my friends was saying that the way that Python does imports is actually one of his favorite features of the language. So he did Ruby for many years and then moved to Python. And he said that the require statement in Ruby is probably his favorite example of technical debt. It's easy to set up, and then you pay for it for the rest of your life. So in Ruby, if you have a require statement, like you require a file, it adds that file to the global namespace for the rest of the program. So you can be calling these kind of globally namespaced objects. You can get namespace overload, and it's very difficult to clean up. And he worked at a company that had a Ruby monolith, and they went public. So they're actually a big public company also in Silicon Valley. And the only way to clean up these kind of namespace overloads are to write a ton of tests to get complete test coverage for your code, and then go start to remove requirements and see where it breaks. And that's how you clean it up. And so he's got 100 developers at this public company that's slowly cleaning up the Ruby monolith. And I thought that was the best description of technical debt I'd ever heard. Whereas in Python, imports are explicit. And so we can know what we have in the namespace for any different module, and we have a lot more control over the namespace. Object-oriented versus procedural. So Python is object-oriented. You can write classes, you can write objects. You can also write procedural Python, but people tend to use kind of a mix of the two. When I moved to Golang, Go kind of doesn't like objects. So Go is very procedural. One of the nice things about object-oriented programming languages is that you have more code reusability. So that's generally one of the features of objects, is, hey, we can describe this thing, and then we can reuse it all over our code base. I feel like I should just take my computer and hold it up for everyone to see. Just hold it.
Because when I'm here, it works.
All right. So object-oriented has more code reusability. However, inheritance can increase complexity. And so Go, as a language, was like, we don't want objects. We don't want to deal with inheritance. Inheritance is too complex. People get into lots of trouble. So Golang removes some of the complexity of inheritance because we don't really have objects. However, we do have structs. And structs can embed other structs. And if you embed enough structs, it looks a lot like object inheritance, but a lot more of a mess. So Go didn't quite get rid of it, despite what they wanted to do, and introduced another element that has kind of similar behavior without being explicit about it, which leads to a lot of complexity, which I think is a great example of how even when you have the best intentions for getting rid of some technical debt in one language, there's usually a reason it's there. So there's a lot of advantages to objects, and trying to get rid of objects, turns out, is very difficult. Community features. So one of the things that I think is really interesting about languages is how the community affects how we write the code and the standards that we have for different code. So in this case, I compared 3 different languages: Python, Go, and JavaScript. So Python is one of my favorite communities. Python has one best way to do things. We have a really cohesive community, and we have a lot of libraries. So we have a lot of community support for open source libraries, solving problems that we can all use. Go has many ways to do things. They have a very cohesive community, but they have few libraries. So they don't have a lot of community support for libraries, so everything's built in-house. And what this means to me, in comparison to Python, is that in the Python world, actually, let's do a poll. And let's go over JavaScript. So JavaScript has, again, many ways to do things. It's not a cohesive community, and it has a lot of libraries. So how many of you write JavaScript for work? A fair amount? OK. How many of you use React? Just keep your hands up. Angular? Mustache? Backbone? What am I missing? Ember.js? Is it here? Just keep yelling them out. Just yell out all the JavaScript frameworks that you use. Yeah. So in JavaScript, there's so many libraries to do things. Everyone's using a different library. There's so many solutions. The community doesn't even agree on standards. JavaScript used to be browser, so people used a lot of global variables, and then it moved to server side, and so people still use global variables, but you shouldn't on the server side. So the JavaScript community, even separate from the language, I think of as being kind of a hot mess. By contrast, Go is a new language. The community is very cohesive. It's a pretty small community, but there's not a lot of library support, and the community doesn't really believe in having one way to do things, and they believe in building in-house. So Go is like, we want to build in-house, we want to have control over our code. However, what that means to me is that as a community, there's a lot of stuff that we're redoing at each company, and that's technical debt that each company is taking on separately and not sharing. Python, I actually think, has the best community around the code, which is that we often have one best way to do things. So how many of you use the request library, for example? A lot of people use requests. We tend to converge on standards, and we tend to converge on best solutions because it's part of the community identity, even as it's part of the language. So if there's one library that we like, a lot of people tend to support it and make it great. Request is used by a ton of companies. It's also used in the background of AWS, which means that we all get to share in the fact that that is a really well-vetted library. We don't have to build that code in-house. We know it probably works, and it works at scale. And because we have that kind of library support, there's a lot of things that we can do quickly and really efficiently. And so there's a lot of technical debt we don't have to take on simply because of the way the community is organized. And I think that's a really interesting feature of Python. It's one of the things I miss in the Golang community, and it's one of the things that the JavaScript community just does not have going for it. And then finally, universal technical debt. Dun, dun, dun. Because you can make a mess in any language. So tightly coupled code is difficult to test no matter what language you're in. Code complexity exists no matter what language you're in. I do think that Python, because it's readable, or because of its emphasis on readability, allows you, and has code complexity tools that you can use, allows you to write much simpler code, whereas in Go I've noticed a lot of very complex code because people kind of fall back on the static typing tools, but you don't have to. You shouldn't write complex code in any language. And then finally, readability and organization are always problems across every language. You can have poor organization no matter what programming language you use, and you can have great organization no matter what programming language you use. Okay, so finally, what can you do about it? I didn't come up with a lot of answers, but I do think that there's a few things that you can think about doing if you want to reduce technical debt working in Python. The first is to look into using MyPy for static typing. This is starting to be pretty well vetted by the community as a way to improve some of the bugs that you see commonly in Python. Use formatting and linter tools aggressively. There's some great tools for code coverage. There's some great tools for assessing code complexity. So it basically will check to make sure that you don't have functions that are too complex. And complex functions are usually really long. They might have nested for and if statements. They might have complex Boolean logic. Rely on Python's strengths, readability and community support. So because we have a great community, when in doubt, you can go ask questions and see if anyone has seen a problem that you're up against before and see if there's a fairly simple solution out there for what you're up against. And then finally, understand design patterns that are important in Python, and I'll talk about those in just a second. And if it's known technical debt, add it to the backlog to track. So if you know you're taking on technical debt consciously, one of the biggest pieces of advice from professional consultants who go in and clean up technical debt for companies is add it to the backlog as a series of tasks to say, we are knowingly making these trade-offs, but in the future, we should address them. So just for fun for this talk, I actually tweeted a friend of mine, David Kramer, started Sentry. How many of you use Sentry? Yeah. So I tweeted at David Kramer, and I was like, hey, David, what are the most common Python exceptions that you see in Sentry? And he got back to me and he actually put it up in a gist, which is linked at the bottom here, and I can send out later, of all of the most common Python errors. And as you would kind of expect, given the static versus dynamic typing thing, these are the top 10 most common Python exceptions, and type errors make up 15% of them. Key errors make up almost 15% of them as well. Attribute errors, so type errors and attribute errors and value errors can all pretty much be solved with static typing. So I thought that was actually a pretty big validation of adding typing to Python. And I found this really great chart that is like a little cheat sheet for the types of errors that you have. So type error, you're trying to use an operator on the wrong type of object. Attribute error, you are calling a method on the wrong type of object. And then value error is you've passed in the right type of object, but it's not working, and there's no more specific error. And then design patterns in Python that you should know that I think will help reduce technical debt pretty quickly, and there's a lot of talks on these, and a lot of people have great opinions on this. But composition over inheritance, so rather than having complex inheritance structures with your objects, use composition. Dependency injection to make testing easier, so pass in dependencies so that you can construct them in tests more easily. And then decorators maintain readability and reusability. And decorators are a great part of the Python programming language. So I highly recommend leaning on those. And then, I can't remember his name, but this user handle at GitHub made a list of Python patterns and has examples of each one of them in Python. So if you go to this github.com page, you can see a list of all of the different design patterns and what they would look like in Python. And I think brushing up on those in any language that you're using so that you have an idea of how to pattern match against problems you're up against and say, hey, okay, we're trying to solve this problem, and there's a design pattern I know about that might make this really easy, is a great way to basically not have accidental technical debt, where you are ignorant of solutions that already exist for your problem. So that is my talk on programming languages and technical debt. My name again is Kate Heddleston. You can find me at kateheddleston.com, and if anyone has any questions, I think we've got about 10 minutes. Thank you.
Thank you a lot. Я напомню, сегодня опять за лучший вопрос книга. I will repeat today we gift you a book for the great questions.
Hi, thank you. When should we fix tech debts? In what time? Product time or our free time?
That's interesting. The best description I've heard of how to fix technical debt is at a certain point you just have it. You just probably have a lot of it. And so probably about 20% of your engineering time should be on maintaining, working down your technical debt. There's a good chance you'll never get rid of it, to be honest. But kind of keeping your code base up to date should be at least 20% of developers' time.
Okay, thank you.
Hi. Thank you for the talk. Can you advise some most useful book, in your opinion, to learn more about this problem, how to work with this problem, to go away from the technical depths once and forever? Thank you.
Yeah, there's no specific books that I know of on technical debt, but the books that, and the web pages I was looking at a lot were on design patterns in general. So there is a book it's called Design Patterns, and the authors are called The Gang of Four. It's very famous. And it's about object-oriented programming. It was written in the 90s, and kind of a lot of the design patterns come from there. That being said, it's interesting when you start to use languages like Go, which doesn't believe in classic object-oriented programming. So some of the design patterns will work, some of them won't, and it's really interesting to see as well how the design patterns map to different languages. So I'd recommend starting there. I'd recommend starting too with design patterns in Python. That's a great way to start doing research on this, because design patterns are effectively a way for the community of saying, hey, we've seen a problem before, and we think that this is a pattern that can solve it. That being said, you can go too crazy with design patterns as well. Sometimes just implementing a solution that seems simple to you is the best way to go, but sometimes a design pattern will clearly help you think about the problem better. So I'd recommend that. Design Patterns by the Gang of Four is the place to start, I think.
Hi. You talked about object-oriented versus procedural programming, but how about functional programming paradigm? I mean, isn't it a way to fight technical debt when you have pure functions, no side effects, and immutable data structures, and so on? Thank you.
Yeah, definitely. I did not add this. I didn't do a bunch of research on functional programming languages because I haven't spent a lot of time in them, but everything I've heard from people who use them is yes. Functional programming languages, that language feature similar to static typing, also helps fight certain types of technical debt. I'm not an expert on it, but that's definitely something that would be fun to research, and ask any friends who've worked in functional programming languages and non-functional programming languages what the differences they've seen are. And if you have opinions, you should totally write a blog post.
Hi, thank you for your talk. My question is, have you seen a difference in technical debt associated with using a particular programming language and technical debt associated with, for example, the domain that you're trying to solve? For example, if you have programmers moving from selling cars to working on a social network, just because they don't understand what it takes to sell a car, do you have to re-educate them somehow on, hey, this is a problem we're trying to solve, and how much time do you devote to domain-specific problems?
Yes, I think there is technical debt based on the domains that you're in, but I think it might have to do, So one of the things I didn't touch on that I think absolutely exists as well, if there's technical debt in code, I think there's also infrastructure debt, so like architectural debt and how you set up your infrastructure. And I think that the domain that you're in the infrastructure has a lot more to do with that. So I was talking to someone yesterday about coupling and decoupling code, right? So that's kind of one of the themes here. Tightly coupled code is hard to test. And he asked a great question, when do you know when to separate things, and like how do you start? So you can have everything together to start with and just say, oh, okay, well, while this is simple, we'll keep it all together and then separate it later. Or you can go to another extreme and you can have two separate services, two separate web services with separate databases. And you can completely decouple the code on an infrastructure level. And we've seen companies do that. And depending on how you abstract it, and people will often do this because of the domain that they're in. They're like, well, we need to decouple this for scaling reasons. But what happens is something that Kelsey Hightower, who is a Kubernetes developer evangelist, calls the distributed monolith. What you have is code that's not actually decoupled, but it's running in separate infrastructure. And so it's highly dependent on each other and really can't function without each other, but you've decoupled it because you probably thought you were going to need to scale one service separate from the other. So I do think that the domain affects technical debt, but I think it can get really complex if you start to add in the infrastructure and the ways that you set up and abstract the infrastructure. I just focused on languages in this one.
Thanks for the talk. Let's say I have a project with a totally huge technical debt. And how do I choose between total rewrite or just massive refactoring?
A total rewrite or just?
Yeah, I mean, I can start over, new project for the same problem, or I can try to fix that one. With how do I choose?
That's a great question. This question is one I think that there are some experts out there who might have opinions on. So there are consultants who professionally go in and help companies pay down technical debt. I don't know as I have a great answer to that question about when you would do a full rewrite versus when you would just incrementally change. So I'm sorry.
Thank you for the talk. When people talk about technical debt, they usually talk about code. What do you think of technical debt in tests, like when you have a huge code base of tests and you're afraid to change it because it will decrease the code coverage, but you don't know the big amount of tests, what they are supposed to test? What to do with that?
Oh, interesting. Yeah, I mean, you can definitely get that. You can have a lot of really big tests that are either testing a lot of things in one test, and you're not sure exactly what it's testing. There can be really complex setup. Testing infrastructure, I know it can be its own beast. I mean, the way I would approach that is I would break things into smaller pieces, just in general. So if you organize things, put things in the same place, reusable setup, and then break things into smaller pieces. But definitely testing frameworks and testing theories is also its own space on like how to test really well. So I would go and I would read a bunch about that.
Thank you for your talk. Thank you guys for the question. Kate, please select the best question. To give a present.
Oh.
Yeah.
Oh my gosh, there were a lot of really good questions.
We can divide page by page, like, or 20% of the book. Like.
I liked the question about domain-specific technical debt. I thought that was a really good one. But I thought all your questions were great.
Thank you.